Right, so we're in another type of motion now. Did this one save? Not yet. Oh, come on. Here we go. Okay. So next lesson is called simple harmonic motion.
Is it hard, this lesson?
All the lessons are hard. Is it harder?
Yes.
Yes. Now it's called simple harmonic motion, but I often write SHM for short. But you should write the full name, simple harmonic motion.
What means hard?
We will get to it. We will get to it. Okay. You have this? Yeah. Continue. Right. That's a lot. A spring, of course. So, this motion that we see when a spring moves is a special type of motion in physics known as simple harmonic motion. So this motion, like this is called simple harmonic motion. Like this. Just like with circular motion.
Like some toys, there is a spring.
Yes, I know this. I've played with toys before. You don't need to tell me this. Just like with circular motion, it is a special type of force that makes this motion. So, it's going up and down, and there's a special force that causes this. And the force, if it's undergoing simple harmonic motion, then the force is proportional to the displacement and acts opposite to the displacement. So before you write that down, let me just explain. Here is the toy, and it's moving like this. What happens is, when this is big, when the S is big, then the force is also big. And when the S is small, then the force is also small. That's what this word means, proportional. Proportional means big with big and small with small. Also, here you can see the S is positive, but the F is negative. And here the S is negative, but the F is positive. So that's what I mean when I say it is opposite. Okay, so this is the picture and this is the definition. This you will need for the exam if they ask you what is simple harmonic motion. So this you need.
Okay, but I need to see so
yeah, but you see what?
Definition. Write it.
It was right there.
No, because I don't.
What?
Cannot see because.
Then move.
Okay.
Yes. So if you can't see there, then sit over there.
Okay. And
you are a physics student. You should be able to solve these problems, okay?
Excuse me.
Yes.
If in the exam have the question about this.
Yeah.
So when I write, I
Go
have
this way around. Yeah.
I have to write
All of this.
yeah.
Proportional. Yeah.
Or I say F.
Yeah.
Bigger is F.
F bigger. Yeah.
I can write that, or I have to write it.
Oh, I would prefer if you use this word. If you said S is big, then F is big, and S is small, then F is small, okay, maybe it's okay. But I would prefer if you wrote proportional, please.
okay.
You should learn this word, it's important. You wrote this down?
Yes.
Yep. Okay, continue?
No, sir.
Okay. Now, of course, you don't need to get this perfect in the exam. For the exam, there's a couple of key words they want to see. What do you think that might be? Proportional. And also, this is important, that it's opposite. So the two key words here is opposite and proportional as key words. You won't get full marks for sure if you forgot one of those words, because opposite is important to show that it's pulling it to the center, and proportional is important to show that the force increases with an increase in displacement. Yeah. So you need those two words. Okay, continue now. Yes, I'm continuing, Mahmoud. Yes. I'll give you one more sip. What's wrong, dude? What? When's the break? After this class? Yeah, just hang in there. Alright, continue now. Okay. Right, so let's have a look at the velocity time graph. And let's try and draw it together. So here we go. Here's my spring. And I pull it up.
And down.
And then I let go. Okay, do you understand?
Mm-hmm.
So I pull it up and then I let go. So I want to make the velocity, and that's in meters per second, and then the time, which is in seconds. Okay. Let's see if we can get this. I pull this up and then I let go. Where do I start on my graph?
Up.
Start here?
It's going to be the highest point.
So I should start my graph here?
No. Little down.
Oh. Here?
No, like little up. Wait.
We'll go up and then we'll go.
No. What?
Here, something like this.
Fine, here.
Yes.
No.
Okay, wait.
No, think. Stop. Think.
Is it down?
Stop. Thank you. When you pull this up
Yes.
and let go, at the beginning, it's at rest.
Yes.
So it's here, no speed. And then what starts to happen?
Jumps.
It gets faster.
Yeah.
So, what way do I move?
Up.
No.
Down.
Down, because the velocity is negative. When I pull it up and let go,
Yeah.
go down.
Yeah.
So, it'll go like this. And it'll go down and down and down and down, and then it will stop and then go back up. So my graph will go down and then it will stop. And this is when it stops here. And then after it stops, what happens? It goes up. So then it gets faster and goes like this. And then it slows and stops again. So here is when it stops again at the top. And then it continues. Until yeah. Huh? Why what? Continues.
No, but it comes in the same height. It will lower.
Yeah, I know. We'll do that later. In real life, it will go like this. Yeah. So I know in real life the graph will look more like this.
Yeah.
Yeah, we'll do that later. Don't worry. If, of course, I said V is positive, then the graph will just look like this. But it's the same idea. Up, down, up, down, up, down. So this is the graph here. It's negative because it's going down. Yeah? And as Furlong pointed out, and as you pointed out as well, this is not real life, because in real life it doesn't continue forever. Eventually it will stop at the end.
Limit.
It has a limit, yeah. Can you just draw this graph? I think will be useful in your notes. This is a velocity time graph for simple harmonic motion in my example. Okay. Continue. Right. In simple harmonic motion, we have three terms. What the heck is wrong with my grammar? Three terms were also used in circular motion. No, are also used in circular motion. They are F, T, and omega. So we use these for simple harmonic motion as well. So again, remember the F is the frequency, how many per second. The T here is the time. The time to go from the top to the bottom, back to the top. This is 1. Yeah. One cycle. Yeah. And the omega is also used as well. And these mean the same thing, except for the omega. What does the omega mean in circular motion? What's the units for omega?
Radians per second.
Radians per second. Are there any angles here? No. It's just going like this. So what's the angle?
It's not angle. Maybe one step.
It's angular velocity.
Yeah, but I'm saying that there's an omega as well, and it's also radians per second.
It's angular velocity.
Yeah, but what angle? There's no angle changing.
What? It's going up and down. The angular velocity changes.
What?
There's no angle. Yeah, it's just going up and down.
Yeah.
What's the angle? Oh, it's a constant 180. Yeah. We'll see it in a moment, okay? It's actually still a special type of speed, but it does not quite mean the same thing. Since there are no angles. So what does the omega mean?
Maybe like from the middle, like.
No, I'll show you. This is a good example to show you what the omega means, the train. This motion here, back and forth, is simple harmonic motion, like the spring. Yeah, like the spring, yeah?
And in the car there is a spring.
Yes. Now listen, okay? This motion here is simple harmonic motion. It's going back and forth. Yes?
Yes.
If I connect this to a wheel, this wheel will turn around.
Okay.
Yeah? The omega for simple harmonic motion is the change in this angle if it was attached to a wheel. Now, I can draw that to show you as well. So, take my example with the spring. The spring is going up and down. Okay? Now, this is how my physics teacher explained it to me, and I'll see what you think of this explanation, if you like it or not. He used a candle, but I'll be more advanced and use a laser. So this is going up and down. So this is the top, and this is the bottom. Okay? Imagine I make a wheel here, and I put a little laser light on it, and it fires a little beam here on the wall. So you see a little red dot here. What will happen to this red dot as the wheel turns around? It'll go down, and then it'll go back up. Like simple harmonic motion. So the omega here is like you imagine there's a circle that's, it's like imaginary. It has an omega. And the omega here is the omega here that matches this motion. Now I know this is a very difficult idea, but I'm trying to explain what the omega represents in the simple harmonic motion. It's the omega in the circular motion that would mirror the simple harmonic motion.
It's almost like the shadow.
It is like the shadow, yeah, with the projectiles,
I'm
yeah.
thinking about how did he explain it to us?
With a candle.
He said you had an old record player
Yeah.
and you put a candle on it, and you see the candle on the wall, and you see it moving left and right. Yeah. So the omega here is what the omega here is. Yeah. So I said I updated to a laser. Yeah. I know this is very difficult, and in fact you don't even need to worry about it, but I wanted to explain why there's an omega in simple harmonic motion. And it's also radians per second. Okay. But look, if you didn't get that, that's okay. It's no big deal. Right. Now there's an animation that will help. If you want to watch the video and then type this link in, there's a nice animation where you can see the relationship between the two. So if you don't understand, you could look at this website later and you can watch the animation that shows the relationship. Okay.
Yeah.
This will be in the YouTube video. It'll be there. Right, so now some terms to write down, please. So equilibrium or origin. Does anyone know this word?
Equilibrium is just like something equals.
Yeah, but as a noun. You can say equilibrium as an adjective, like it is in equilibrium, means it's balanced. But as a noun, the equilibrium means the center, the origin. The center. Yeah. So this is the center of the motion. Okie dokie, yeah. Right, the next word, amplitude. Does anyone know this one?
I'm not sure what you said.
Amplitude.
Not even Siri knows it.
Not even Siri knew that, yeah. Amplitude. What's
It's,
no?
I think it's frequency upon time.
No, give me like the meaning physically.
Like how it's formed?
No. Amplitude? No.
I remember I took it, but I don't remember what.
I'll tell you, look. This is called the origin,
Yes.
and it's moving up and down, up and down, up and down, yeah?
Like waves.
Like waves. The amplitude is the maximum displacement. So the A is the maximum S. Oh, dude, you did this last week in ESAP. Son of a gun. All right. Amplitude, the maximum displacement. You see how important the ESAP is?
I have a question. Why don't you teach it?
Because I'm a busy man, and I see enough of you. And I see enough of you per week. I don't see more of you.
That's so quick, like that.
The maths and physics, yeah. And 6 hours of you is enough, trust me.
10 hours of health and science. Yeah.
6 hours with you is enough per week.
Oh.
Yeah.
And now beginning you get all what you need.
Exactly. Something like that.
For a day, you were like, what? No, please.
Don't make me. Right, next one. Okay, velocity, you know velocity. It's the same. Yeah. Angular frequency, you know this as well. It's the same. Frequency, that's the same. Periodic time, that's the same. So actually only two are new words. Equilibrium and amplitude. The rest are old words. You don't need to write them down. I'm just saying that they're the same. Okay. Are you writing them? You want to write them down?
Yes.
Okay. So just like with the circular motion, there's formulas as well. Yeah. Continue. I need to go on, Mahmood. Okay. Now let's have a look at the energy graph. When the mass is at its maximum displacement, it is at rest. So what is its kinetic energy?
Yeah.
0. Yeah. So if we look at if we imagine this is the x. So if I make a graph, here is the x and here is the energy. So let's look at the kinetic energy. If the x was A, what's the energy? Big or small? If the x was A?
Small.
Yeah, in fact 0. Now what happens when the x gets smaller? What happens to the kinetic energy? It gets bigger. When do you think it's biggest?
When it stops,
When it's
When it's at the middle of the motion.
not when it stops.
Yeah, that's no, because when it changes direction, it must have stopped, and then it's back to 0. So here, no kinetic energy, more, maximum, less, 0. More, maximum, less, 0. So the graph looks like this. It's maximum at 0, and then it's again it's no energy at minus A. When it's down here, no kinetic energy. Now what about potential energy? So when the spring is pulled very big, there's lots of energy in the spring. Because if I let go, what happens? Yeah, it turns to kinetic. So it's the opposite for potential. When it's very big, this is kinetic energy. When it's very big, the potential energy is also very big. So here, it's very big. And then when the spring is small, there's no energy in it. So the graph is the opposite. When I add the two together, I get this graph. Constant energy. This is PE plus KE. So when the kinetic is small and the potential is big, the total is the same. Like here, when this kinetic is big, the potential is small. When I add the two together, I get the same total. That graph is ugly. Here's a nicer graph. So here is the kinetic energy. When the x is big, the kinetic energy is small. But the potential energy is big. And they have an opposite relationship. As you know, when the kinetic increases, the potential decreases because it converts. Yeah. This question they've asked you in the exam a few times to draw this graph. So this is the energy graph for simple harmonic motion. Please draw it carefully. This is kinetic, this is potential, and this is total. Okay. Okay, can I continue? Yeah. Right. So now we can have a look at maybe some more graphs. You don't need to draw these. I just want you to have a look at them.
Okay.
So here, this graph is displacement, the S.
The sun.
This one is S. So you can see, of course, the S goes up and down, up and down, up and down. This graph is velocity. Again, the velocity goes up and down, up and down, up and down. And lastly, the acceleration, also the same. It increases, decreases, increases, decreases. So the graph, you can see how they're all similar. Up, down, up, down, up, down, up, down, like this. Okay. So we have some formulas, and just like with circular motion, you know, all the questions, you just need to use the formulas. Some of the formulas are the same. So for example, the first formula is exactly the same. T equals 1 over x. So if you can write this down, this is formula 1. Next formula is also the same. T equals 2 pi over omega. Yeah. Next formula is different now. The acceleration is not v squared over r. Now the acceleration is minus omega squared s. And the reason, what's the reason for the minus?
Because it's less or
No.
small.
No?
It is opposite in direction.
Yeah, opposite direction. Because remember we said when the S is big and positive, the F is big and negative. So the minus is only there to show you that if the S is this way, then the force is the opposite way. Okay? Now, the next formula, there's 2 of them, and it depends on where you start. Let me show you. Imagine the example with the spring. I pull it up, I let go, and it goes up, down, up, down, up, down. Okay? Or, I don't pull it. Instead, I come along and I flick it. I go like this. So the first one is I pull it to the maximum, and I let go. Or, I keep the ball in the center, and I make it move from the center. So the 2 choices are, it can start from the middle, and I can go flick, and it goes up, down, up, down, up, down. Or the second choice is I can pull it to the top and let go, and then it goes down, up, down, up. Okay? So this one starts at the center, and this one starts at the maximum, at the amplitude. Yeah?
How do you start in the center?
Flick it. Flick. You know this word?
Push it up.
Push it up. Just go. Give it a hit. Make it start moving.
Hold it to the maximum, small.
Yeah, that's it. Yeah.
Okay. Just small.
Yeah. Give it a little. Just give it a flick. Make it move. Don't pull it and let go. Just give it a flick.
How did it make?
Yeah. So like it's sitting here. So instead of pulling, I don't have a spring, but you could. Yeah, oh, nice, nice. So your 2 choices are the first one, or the second one first. I'll do this one, okay? You can pull it up and then let go, and it goes like this. Or I can come. Well, I can't really do it here. Or I can come along and flick it, and it moves up itself, and then down. Yeah.
Yes.
You can imagine it. You can use your imagination. Thank you. So, if it starts from the equilibrium, then we have this formula, S equals A sine omega. But if it doesn't, if it starts from the amplitude, then it's cos instead of sine. So this one we use sine, and this one we use cos.
Center of sine.
Yeah. Now let me tell you how to remember this. There's a nice way to remember. Look. Please look for one moment. This one, you can think about it starting on the inside, and this one here starts on the outside. What letter is this? I. And what letter is this? O. And what letter is this? I. And this one? O. So you can remember it this way. Outside is cos, and then from the inside is sine. This is the way to remember. Okay?
What's capital A?
Oh yes, I'm sorry, I should have said that. Capital A, well no, I said it earlier, amplitude.
Oh, it's the amplitude.
It's the amplitude, yeah. Okay, next formula. Is the V. Sorry, ready for the next one? Yeah? Now wait, before you write it down, just look. The V and the S, they're always opposite, okay? So if you use sine here, use cos in the other formula. Or if you use cos here, use sine in the other formula. And the V is velocity. It's A omega cos omega t. Or sine omega t. Yeah. Okay. A omega cos omega t. Yeah. You have this? Okay, next formula is, I think it's probably for A. No, it's another formula for B. Now this formula, the reason for the plus and minus is because you have the square root, and it could be going left or right, so you need to choose if it's plus or minus, and it's another formula for V. What is in this formula that's not in this formula?
Time.
Time, really. So if you know the time, you could use this. And if you don't know the time, but you know the S, you can use this one. Yep.
You don't know T and S?
Oh, if you don't know T and S, that's a problem. Yeah. That's a problem, yeah. Right, next is the formula for potential energy. It's half m omega squared s. And then, no surprise, the next one will be kinetic energy. But of course, I don't even know if I gave it to you, because kinetic energy is going to be the same. Yeah, actually I didn't even bother. Kinetic energy is still a half m v squared. The potential energy is a half m omega squared s. So look, if the S is big, then what happens to the potential energy? It's big as well. If the S is small, potential energy is small as well.
Potential energy is equal to kinetic energy.
Again, the potential energy, it's a bit like with this one. We said the potential energy here equals the kinetic energy here. Likewise with the spring, if I pull this up, or if I pull it across, the potential energy here equals the kinetic energy here as well.
What is the formula for it here?
For potential energy?
Yeah. No, for kinetic energy.
The same. Half mv squared. Yeah. Note in the last equation the S is... Sorry, I didn't finish the slide. I left it on a cliffhanger. No, in the last equation, the S is unknown. I don't know why I started typing that and not finish it.
It's big when guys use it.
Maybe.
I think I was just saying that the F is the distance from the equilibrium. But of course, you already knew that, so I don't. Maybe that's maybe. Yeah, maybe I'll just delete that. Yeah, I don't know what I don't know what I was going to say there. We'll just get rid of it. Okay, so let's continue then. Now, this is what two of you were saying earlier. Oh, hang on, let me just get rid of my. Okay, we'll just remove that. Right, so in the real world, we know this is what the graph really looks like. The equations here are too difficult for this level of physics, but at university, when you study physics, you will study the equations for this motion. This is in university physics.
No, I mean in university, the studies will be hard.
Yes? Oh yeah, of course. So here, you will do this at university. Yes? Now this is called damping.
What?
Damping. This is the name of this type of motion. Is called damping when it goes like this. So all I need you to do is write down the name with the picture to help you remember. Damping. That's real life. Okay, next. Continue? Yeah. Okay. Oh yeah. I wanted to find a picture online of this, but I couldn't find any picture online for, that should actually say a forced harmonic oscillator. So, can you write the title down and then I'll draw it?
Okay.
And I could not find a picture online.
Maybe
I searched and I searched on Google. I could not find a picture of
maybe
this.
the other Google, what's name Google?
Scholar.
Yes.
No, no good. I have a picture in my book at home, my physics book from university. I could scan it in, but no.
I have a book of physics, but it's like, it's not here, it's in UAE. I can bring it when I come back.
Don't worry, I have many books at home. That's okay. Right, I'll try and draw this to show you what it is, okay?
Yeah.
Yes? Right. Look. Look. This is simple harmonic motion. So here, this will go up and down, and it will have a t as well. So maybe here the t equals 2 seconds or whatever, and then the omega would equal 2 pi over 2. So in this case, the omega would equal 3.14 radians per second. Okay. Now here again, let's say the t equals 2 seconds. And what would the omega equal? Again, it would be 3.14 radians. Oh, why did I do this? Disgraceful. S minus 1. S minus 1, okay. Right, and then here, this is what the force part means. I should have said forced, actually. Forced. That's when you move this part as well. So you can picture your hand here, and you're moving this up and down, and you're doing this with some time as well. Let's call it t0, let's say equals 4 seconds. So the bottom is going like this, but then at the top you have your hand and you're going like this as well. Okay. Now my question is, how do you think this affects this? So for example, let me try and make a table here. We'll have the bottom, we'll have the T, and the top we'll call it T0. Okay, so let's just say that this, I don't know, we'll just say it's 2 seconds. So if the time here, if I have no movement, then this of course doesn't change. I want to know if it will get bigger, smaller, or stay the same. So let's say my T0 is very big. So that means, very small. If it's very small, am I moving fast or slow?
Slow.
Fast if it's small, because the time is quick. So what do you think happens to this one at the bottom?
It goes slow.
Bigger or smaller?
Smaller.
So you're going to say it's bigger? Yeah, okay. And then what about if the T0 is big? So that means I'm moving it slowly here.
The other one will be small.
You think the other one is small? Yeah. Now what do you think? You think it'll be big? Okay.
Yeah, it will be big and the first one will be.
And you think the first one will be small? Okay, great. Now the good news is you're both wrong.
Can I make a comment before?
Yes, go on.
Does it depend on the movement? Is it like the weight, if you have the weight like this, it will be on?
Okay, so you think it also depends on the timing.
On the
So
timing.
if you go up and it goes up,
That makes it slow.
yeah, and then maybe in the opposite way.
Makes it faster.
Yeah, good. Also wrong. In fact, believe it or not, this does not affect the time. Now that might be difficult to believe because in your mind you imagine that if I'm doing this here, it's going to change the time at the bottom. And in fact it doesn't. The only thing that gets changed, does anyone want to suggest what might change? Yeah, the only thing that gets affected by it is the amplitude. So the motion here can change the amplitude here, but in fact the time, the frequency, and the omega, they all stay the same. Now you should look confused. It seems surprising.
Yes.
It does, because you feel like they should all change. But they don't. Only the amplitude changes. Everything else, T, F, and omega
But
stay the
the
same.
A is not here. Oh.
Yeah. Okay?
The amplitude is the height.
The maximum height, yeah. Yeah. It's hard to imagine, but I mean, you could do the experiment. For example, if you had the spring and you release it and then you time it, and it goes up and down and you time it, then maybe you have a little machine that moves it up and down. So you do the experiment again, you pull it down, you let go, and the machine is shaking on the top, and you time it, and it goes up and it goes down, and you see that the time is the same.
But the question is confusing.
I know it is, yeah. Now, we don't have to worry about this for the exam. All I need to do is just mention that it's unaffected. And that will be important for something later that we'll do. So the idea is what you need here, that the forced harmonic oscillator, the T, the omega, and the F does not change, only the A changes. Please make note of that, it's important.
What's right?
What I just said. In the forced harmonic oscillator, the T, omega, and F do not change, but the A changes.
Does the A change, yes?
Yeah, yeah.
throw a guy with 2 hands, like
And just before we continue on, note that the F does not depend on the A. Well, that's not really what I wanted to say too much. I'll just change that a bit. So what I wanted to say here is that the F, omega, and T does not change from the forced harmonic motion. Only the A changes.
What's the dollar sign?
Yeah. Huh?
What's the dollar sign?
To make it the match symbol. Okay, now I want to show you how it changes. So, here's my man here, and he is moving on the top, and let's say he moves with frequency F. So, for example, if the F is 2 Hertz, then that means in 1 second he goes up, down, up, down.
Yeah.
Okay? And then let's say we have the motion here, and let's say the frequency here is 3 Hertz. So in 1 second it goes up, down, up, down, up, down. Okay? So let me just call this one F man, and let me call this one F ball, for example. And there is a few possibilities here. We can make the F from the man bigger than the frequency for the ball. We could make them the same, or we could make it smaller. And my goal is I want to make the A bigger. So my question is, we don't need the examples, what should the man do to make the A bigger here? Should he A, make his frequency bigger, so he's going very fast? B, should he make the frequency the same as the ball, so he tries to match it? Or C, should he move very slowly, slow frequency?
To change what?
He wants to make the A big down here.
So it will be B.
Correct.
Yeah.
This is the one that will make the biggest change in the amplitude. So this is the one that makes the most change. You don't need to write this down, but I will mention this again later.
Okay, but like we need to understand it.
Just understand it for today.
This
Yeah.
makes sense.
This makes sense
Yeah,
to you?
like the other one, this makes sense.
This makes
Yeah,
sense. Okay,
this
good.
one.
Good. All right. Now let's have a look at some questions. So, draw or write, and then I'll do it.
Draw.
Okay, fine. Okay, do we have a drawn?
Yeah.
You drew?
Yes.
Why not? So, what happens here is you have the spring, and then the boy pulls it down and lets go. So then it starts going up and down, up and down, up and down like this. The time equals 0.5, and what else do I tell you? That's it. Okay, so if the t equals 0.5, the omega will equal 2 pi over t, which will equal
It will be 2 pi
12
over 0.5.
5, 7 radians per second. Yeah. And do I give you anything else?
Yeah, after 1 second left. How fast is it?
How fast spring will be after 1 second.
Okay. So, we have two formulas for the speed. We can say V equals, now, is this one inside or outside?
Inside.
Actually, I kind of drew that wrong. It's outside because he pulls it down and lets go. So here we should use cos for the S. So then for the V we need to use sine then. So the V equals A omega sine omega t. The other formula we have for V, what was it? Square A. Yeah, A omega square root. Square root.
V squared minus
A squared minus S squared. Yeah.
How do you know it's cos?
I don't think that
It starts on the outside because it pulls it down.
Omega or
It's
plus or
plus
minus?
minus omega.
No A, sorry.
If he pulls it up, it's the
If he
opposite.
flicks it up, it's the opposite, yes. You know this word, flick? This is flick.
In the exam you will say it's flipped or?
Yep, yep, yeah. Well, they might not say flick. What other verbs could we have? Hit, knocked, touch.
If it's not pulled, then.
Basically, yeah, if it's not pulled, then it's the other one. Yeah. Yeah? Yeah. Okay. I forgot what I'm asking for. Oh, the V. Yeah. Now I give you the time. I say, well, firstly, what's the omega? So I've done this. What? Are you focused? Okay. And then I ask you, how fast is it moving after 1 second? So 1 second later, when the t is 1. Yeah. I think I left out some information because I didn't tell you how far he pulled it down, did I?
Have the answer.
Yeah, so I'll just add that in, sorry. I'll say a boy pulls a spring down 5 centimeters and releases. Okay, so here the A is 0.05. Okay, so which formula should I use to get the B?
The first one.
Yeah, the first one, because I know the A, I know the omega,
And the sine.
and I know the sine, of course, and the omega and the t. Stop. Important warning. Warning. Warning message. Listen to this warning. Your calculator must be in radiant mode, because for both the simple harmonic motion and the circular motion, you must use radians. On your calculator, you can change the mode to radians. For me, I press Shift Mode 4. Did you do that?
Yeah,
Shift
I know that.
Mode 4. Do you have a calculator? Yes? Where's your calculator? Come on.
I have a calculator.
Okay, on your phone?
No.
Okay, fine, that's okay. You don't need it right now. Alright, so let's calculate. A, what's A? 0.05. Omega? 12.57. Sine, omega,
0.57 multiplied by 0.5.
no,
Sine.
multiplied by 1.
Yeah.
1 second after 1 second.
So the V is a small number. The V equals 2.28 times 10 to the minus 3 meters per second. Or if you prefer, the V is 2.28 millimeters per second. This is the answer. Yep. Okay. Continue. Yep.
Can I go to the toilet?
We are going to be finished in 2 minutes. Can you wait 2 minutes?
Yes.
Great. I have only one more example to do. So, Do you know this word from chemistry, a molecule?
Yeah.
Yes.
So a molecule is vibrating with frequency 8.25 times 10 to the 14 hertz. So what you have here, you have a molecule. What molecules have you done in chemistry? Give me an example of one. H2O,
H2O.
most common one, yeah. So something like H2O, and these, I don't know if you've done this in chemistry, these vibrate. Have you done this?
No.
No. So if you look at something like H2O or whatever, it vibrates. So in fact, the motion is simple harmonic motion. It vibrates.
Like the water vibrates.
The water molecule vibrates. Yeah?
Yeah.
Okay. So in this question, I tell you that the frequency is 8.25 times 10 to the 14 hertz. So the frequency is 8.25 times 10 to the 14 hertz. And I also tell you that the amplitude is 74 picometers.
Pico is minus.
You might have to look this one up if you forgot it.
5. Is it?
Nope. The amplitude is 75 picometers, which is 75 times 10 to the minus,
12.
9.
I think it's 12. Or is it 10?
12.
12.
Yes,
Is it?
I think.
If Mahmoud says it, I think
Yeah.
it's off.
No, I think he's right. I think it's minus 12. Do you want a quick Google? PICO meter.
Yes.
Now, why is the amplitude small? Well, because it's a little molecule
Yeah.
vibrating back. Good, okay. Right. So we know the A and we know the F.
And the T,
And do we know the T?
because it's always in the...
Yeah, we can get the T then. Yeah. So what I want everybody to do for me is get the omega. I want you all to calculate the omega. I'm going to actually change this a little bit. What is the omega? What is the maximum velocity? And what is the maximum...
But the D is not given in the question.
No.
So how we will
Please go back
to know the answer?
I changed the question a little bit. So the information is F equals 8.25 times 10 to the 14 hertz, and the A equals 75 times 10 to the minus 12 meters. Okay, did we get the omega? No?
I think it's F.
Not quite. Omega is 2 pi over
5.18.
T. And what's the T?
Yeah.
We don't have the T, but T is 1 over F.
Oh.
So it's 2 pi F.
1 over 8 or...
Hang on, I'll check it now.
5.184 but below 10 minus.
So the answer is 5.184, yeah, times 10 to the 15 radians per second.
Okay, from where you got the F, like the number?
I'm having multiply by
The
10
number
minus
of
11.
F.
It's given. This is given.
Oh, so this one.
Okay. Now I'm going to change this question a little bit. I'm not going to ask for this. Instead, I want to know what is the maximum velocity. So let's do this one again. I want to know the maximum velocity. We have two formulas for velocity. Let's look at both of them. The first one, V equals A omega cos omega t. Or we have V equals A square root...
No, it's not.
Omega.
Plus and minus.
Oh, sorry. A plus or minus, yeah.
Plus or minus omega,
Sorry, omega square root
A squared minus
Minus
S
S
squared.
A squared minus S squared. Now, I want to know the maximum V, the biggest it could be. If I look at this formula, does this change? No. Does this change?
No.
No. Does this change?
No.
Yes, because it changes if the t changes. Yeah? Does anybody know what is the biggest cost can be? The biggest value cost can be? It's 1. So you could say the maximum the velocity could be is a omega.
Yeah.
That's one way to think about it. Or, if you look at this formula, this number here, I want to make this maximum. Does this stay the same or change? Same here? Same here?
Change.
Changes. If I want to make this big, then what should the S be? Small. In fact, what should I make for S to make this maximum? 0. So you get V equals omega square root A squared. V equals omega A. That is the same formula. So the maximum velocity is simply the amplitude multiplied by the omega. Do we know this? Yes, and do we know this now? Yeah. So let's calculate. What did I say the A was? 75 pico, wasn't it? Yeah. And the answer is 388,800 meters per second.
So if I have a question, like in an exam...
This is a very common exam question, this one, the B.
So to find the maximum...
Yes.
I just multiply amplitude by omega by...
Yeah.
Without...
You don't need to explain where it came from, but I wanted to show you how to get that result.
Okay.
Yeah. Right, lastly is the maximum acceleration. What formula do you have for acceleration?
Why I'm having the golden answer?
Oh, I don't know, maybe you typed it in wrong. Maybe I typed it in wrong. It's nearly lunchtime, we're hungry. No, we didn't need to use sine or cos here. It's okay, I need to do the last part, the acceleration. So what's the formula for acceleration? Omega squared s, and I don't care about the minus because I just want to know how big it can be, not the direction. So, if I want this to be maximum, can I change the omega?
No.
No. Can I change the s?
Yes.
Yeah, what's the biggest s can be?
1.5 something.
Two amplitude.
Oh, you're close. 1 amplitude. Because the s is the distance from the center, and the biggest it can be is a. The amplitude, right? So the maximum acceleration will just be omega squared a, which equals. Where's my omega? There it is. 5.184 times 10 to the power of 15 squared. That's huge, but the amplitude is tiny. Still, whoa, hang on, that's huge. Let me check that again. Okay, it's a big number. It is a big stinking number. 2.02 times 10 to the 22 meters per second squared. Okay. Homework questions? There we are.
So the lesson,
One more lesson?
what
One more. Yeah.
what's the name of the lesson first?
Mahmoud, I'm tired and hungry, please. You know the name of the lesson.
Okay. So let's not ask the movie. So no need for fiction.
Take the bag. Take the bag. No, okay.
Yes.
Anything?
Huh? I'm just tired. Okay, closing this now.